if you study a pendulum, you find that the pendulum is doing what looks like simple harmonic motion also. It turns out it's not exactly simple harmonic, but it definitely looks like a mass on a spring, right? So what I want to do is investigate how similar this motion is to simple harmonic motion, what might be the limits, and let's get mathematical with it a little bit. So to understand a pendulum, I think the best thing to consider is the energy of the pendulum system. So I'll put a ceiling here, or somebody holding the pendulum bob, and I'll put the string here, and we'll say that there's this purple thing, maybe it's a plum here, is our pendulum bob, and the length of the string from which it's dangling is L. And then I guess I'm just really interested in what the potential energy of the pendulum is. Let's get some blue out here. The potential energy of the pendulum is m times g times h. So we need to kind of think about, maybe throw an angle in here. The height is certainly going to depend on the angle. Let's call it theta. The mass of the pendulum is going to be known. We'll just say that it's a pendulum of mass m. And maybe g will be a constant for our purposes. So we need to figure out how high up the pendulum is above, well, whatever we decide to call the 0 point. It might be reasonable to call the 0 point right down here. In that case, we can continue this dotted line and say that this is a height of 0, and this is a height that we're going to call h. h equals, I don't know, we could call it h1. Or maybe that would be the maximum height. It doesn't matter so much for our purposes. So we're trying to figure out what h is, and it depends on the angle. It's just a little bit of trigonometry here. We can put a dotted line right here. We know that this is a right angle. And then we can do, oh man, what are we trying to find? We're trying to find h. That turns out to be the distance between the equilibrium position and where it is right now. And we have to know, in order to do that, we have to know this distance to here. Turns out that's just the length of the string L. All right, I guess I'm assuming that we're going to the, I'm calling L all the way to the end of the thing. Strictly speaking, we'd probably want to go to the center of mass. Maybe I should scrap the whole thing. No, I think you guys can handle it. We should be going to the center of mass for this. So we're trying to find this distance right here. I'm going to call it out a little bit over here. This is our distance h, and notice that there's an L. This distance h must be L minus something. This distance minus that distance right now. Now that distance right there, that's just L times the cosine of theta. Get the blue marker, come back over here, L times cosine of theta. That's the distance between there and there. Of course, center. Yep, okay. So we'll put it back and consider that this is L minus L cosine theta. This is something you'll have to do in AP problems all the time. It's just L times 1 minus cosine theta. Check the units. That's reasonable that it would depend on length, and this is unitless inside of here, so h is that. So the potential energy then we can write is m times g times L times 1 minus the cosine of theta. All right, let's work with that result. I want to graph this function. I'm trying to graph 1 minus cosine of theta, and it's going to look like this. Well, it depends on angle, so this is going to be as depends on angle. And it's going to be the potential energy, and it comes to a maximum value of, what is this cosine theta? Cosine theta is 1 at theta equals 0. So if theta equals 0, this value should be at 0. That is the minimum potential energy when it's at the equilibrium location. That makes sense. So for large theta, it's doing this cosine function. Since we're at 1 minus the cosine of theta, and theta is getting smaller, cosine theta is getting smaller, we're subtracting less, it's actually going to be this lovely curve that looks like this. And that, I guess, the fact that I'm making it outside of theta equals, maybe even outside of theta equals 90 degrees is kind of ridiculous. These would be the bounds on actually using a pendulum in any meaningful way. We'd bring the bob up to here. Up there is just kind of silly. It would fall straight down and bounce around a lot. But I want you to notice that this graph is not a parabola. And we know that if potential energy is parabolic, then we've got a mass on a spring, because we remember this other equation, the potential energy of a spring is 1/2 kx squared, which is a parabola that opens up. But notice how similar this graph looks to a parabola. In fact, in a certain region, there's a little bit of overlap. Let's be strict about it. This is U for the spring in purple right there. Maybe purple's not so clear, I should put a pink on top of it. This is U for the spring, and it's very similar in some region to the gravitational potential energy of a pendulum. Of course, they only meet at one point. They're not actually overlapping, but they're very, very close to each other. So we're going to investigate just how similar. Just how similar these guys are. Let's find out. To do it, we need a sketch of a pendulum bob again. Here is the pendulum bob, and now I'm going to be more careful. I'm going to go to the center of mass, and that's the length L, and we can define again some theta right here. And we know that the path that's been followed, we know that distance from the equilibrium position, we can define that distance to be s. Now, of course, s is just L times theta. That's the definition of arc length, right? If you've got some angle in radians, and you can bet that we're in radians. Now, there's a force on this mass, and the force is the restoring force. To some extent, the force is the restoring force, and that force is m times g, all right? So here we go. So I want to look at this force m times g and figure out how much of it is restoring force and how much of it is just providing a force that will cancel this tension here. So I'm going to look at the tension in the rope, and I'm going to resolve this force, this weight, in terms of the tension. So this force right here, this component of the weight, is canceling tension. This is m times g times, well, what's that angle right there? Is that the same theta? You bet it is. So this is m times g times cosine theta. And this sucker right here is m times g times sine theta. Can you tell me which component of the force is providing the restoring force in this situation? Our restoring force right here is m times g times sine of theta. Very good. This is the restoring force, and this is just equal to the tension, assuming it's not moving. Now we have to be really careful. If it's not accelerating at an instant, then we can say that. If it's not accelerating centripetally. But I guess m times g would not be the tension down at the bottom because it is accelerating. I don't want you to think that we can simplify any of these things. It's just tension when at turning point. Yeah, let's be careful about this. Very nice. Okay. My point is, our restoring force is known. Our restoring force is m times g times sine of theta. Now this theta function, the sine of theta function, is very interesting. I want to teach you about something called a Taylor series. It's a way to expand a function around a certain point in function space. Check it out. Sine of theta is actually defined this way, and this is how your calculators do it. It is theta minus theta to the third divided by 3 factorial plus theta to the 5th divided by 5 factorial. Can you see the next term? Theta to the 7th divided by 7 factorial. You can certainly give me the next term. Theta to the what divided by what factorial? Yep, you bet. And it goes forever like this. This is true when theta is small. Now, what I mean by small is less than 1, because if theta is less than 1, then every one of these terms is pathetically small. Consider some number less than 1 to the 9th power. That's a very, very small number. And then you want to divide it by 9 factorial, which is one of the strongest growing functions known to man. Holy cow. We've got an extremely small correction in each subsequent term. Over here, this term is the only one that we need to consider right now. For very small angles, we can assert that sine of theta is pretty much the same thing as theta itself. Now, I want to define theta, because we're going to use the fact that sine of theta is just about theta, so we need to know what theta is. I'm going to use this equation right here to define theta. Theta equals s divided by L, right? Right, okay. So let's take this and we'll say that sine theta is approximately the same thing as S divided by L, because sine theta is just about theta. Now this is cool, it's unitless, right? The arc length divided by the length of our pendulum string, and then we can write the restoring force again. So I think I'll go purple for this. F restore, in this case, well, we said that the restoring force is m times g times sine of theta. But now we're saying sine of theta is S over L. So I'm going to write it as m times g divided by L times S. And this restoring force has a similar form. This is the restoring force for a pendulum and for a mass on a spring. The restoring force is very similar form. F restore, I'm not talking about which direction it is, I'm just talking about magnitude. It's the spring constant times x. So both of these have a displacement times some resistance to being screwed up, right? So let's think about this. If it had more mass, then it'd be more resistance to being lifted up like this. If we had a tighter spring, it'd have more resistance to being stretched in one direction. And if baby G were greater, then we'd have more resistance to being stretched in a direction. In fact, this is a little subtler, but if L were longer, it would be easier to displace a little bit along an arc length. I hope that this kind of feels like a spring constant to you. Okay, so I'll put it in quotes. K is our spring constant. Now we've got some interesting results. If we establish that K, in quotes, is actually equal to mg over L, then we can say, well, we know about period, right? We already know about the period of a pendulum. Period of a pendulum is, sorry, the period of a mass on a spring. That's 2 pi times the root of m over k. We can plug in this k that we've got. I'll put some quotes around our k. And we can plug in this new k. Oh boy, this is going to be fun. This will be the period of a pendulum. No longer the period of a mass on a spring as we derived it, but the period of a pendulum is then 2 pi times the square root of m divided by all this stuff. So I've got to put, oh man, I've got to put an L up top, and I've got to divide by mg. Ooh, look who gets to cancel. Okay, pink. Check it out. We now have 2 pi times the square root of L over G. You'll recognize that as an equation on your sheet, and that's where it comes from. So we've got these two beautiful equations. Here, the new page will be exclusively beauty. T for spring is 2 pi square root m over k. T for pendulum is 2 pi times square root L over G. Now look at this. This is very interesting. The m is a tendency not to get screwed up, right? And the L is a tendency not to get screwed up, right? mg over L, mg over L. Cool. And so the G is sort of what's causing the restoring, and the K is sort of what's causing the restoring. So this is what's making the period, I guess if you have more restoring, it's making the period smaller, right? And if you have more resistance to being restored, then it's making the period longer. Fascinating. Fascinating. I really like it. But this is a simplification because we've assumed that all the mass is at a single point. See? We assumed all the mass was right there at that single point. So that simplification is not always valid. And I'm not going to derive this, but I'm going to tell you that T for a physical pendulum, T for a physical pendulum is just slightly more complicated. It's going to start out the same, 2 pi times the square root of L over G, but it's modified by an additional term, which is all inside the square root, so that may be awesome. We're going to use, oh, instead of that L, shoot, I don't want the L there. I want a lowercase l. And instead of just having 1 out here, I'm going to multiply by the root of I over m times L squared. Notice this format here, ml squared, is very much like the format for the rotational inertia. A physical pendulum would be something like your leg. And if this is your hip, it's the pivot point for the physical pendulum, and L is the distance to the center of mass. So that's right there. That's L. That's lowercase l, the distance to the center of mass for your leg. Then you have to also know the moment of inertia for your leg, which depends on all of the distribution of the mass of your leg. So it's a slight modification for a physical pendulum, and it leads to some really interesting results. In fact, I've seen independent labs where people modeled runners' legs as physical pendulums and their arms and got some really cool results. That's it. And let's get mathematical with it a little bit. So to understand a pendulum, I think the best thing to consider is the energy of the pendulum system. So I'll put a ceiling here, or somebody holding the pendulum bob, and I'll put the string here, and we'll say that there's this purple thing, maybe it's a plum here, is our pendulum bob, and the length of the string from which it's dangling is L. And then I guess I'm just really interested in what the potential energy of the pendulum is. Let's get some blue out here. The potential energy of the pendulum is m times g times h. So we need to kind of think about, maybe throw an angle in here. The height is certainly going to depend on the angle. Let's call it theta. The mass of the pendulum is going to be known. We'll just say that it's a pendulum of mass m. And maybe g will be... If you study a pendulum, you find that the pendulum is doing what looks like simple harmonic motion also. It turns out it's not exactly simple harmonic, but it definitely looks like a mass on a spring, right? So what I want to do is investigate how similar this motion is to simple harmonic motion, what might be the limits. So we're trying to figure out what h is, and it depends on the angle. It's just a little bit of trigonometry here. We can put a dotted line right here. We know that this is a right angle. And then we can do, oh man, what are we trying to find? We're trying to find h. That turns out to be the distance between the equilibrium position and where it is right now. And we have to know, in order to do that, we have to know this distance. Be a constant for our purposes, so we need to figure out how high up the pendulum is above, well, whatever we decide to call the 0 point. Might be reasonable to call the 0 point right down here. In that case, we can continue this dotted line and say that this is a height of 0, and this is a height that we're going to call h. h equals, I don't know, we could call it h1, or maybe that would be the maximum height. It doesn't matter so much for our purpose.